before the coffee break. Yeah, so the poster session will be right after Tielens talk. And just a brief, just to start announcing already, we're going to have a group picture, but on Thursday. I'm just telling you so that you prepare. In the afternoon during the coffee break, we'll have a group picture. So do come on Thursday. Do come every day, but anyway, come on Thursday afternoon. And so, Tielens, the floor is yours.
Okay. This third lecture will be on interstellar pars, so large molecules in space. And let me start off again with the take-home message, so that if you had a big lunch, you can now go to sleep afterwards. Large par molecules, large polycyclic aromatic hydrocarbon molecules containing some 50 carbon atoms are very abundant and are widespread in the interstellar medium. And these molecules are excited by UV photons and then relax through the emission of infrared photons. And it's those infrared photons that we detect and that tell us that these species are present. Pars are the key to ionization. I'll talk about that today as well. And the energy balance of the interstellar gas. And actually, I'll talk about both of those today. And then there is a rich chemistry that's initiated by these pars as these pars are being dissociated, and that's another aspect that I will cover. The last part, how pars are formed in stellar ejecta, I'll skip over because that is really a topic in itself, and that would take too much time. So let's start off with this spectrum, these spectra. These are infrared spectra from about 3 microns to 20 microns. These were obtained by the ISO satellites, and they show broad emission features, here indicated by these red shaded areas. These are atomic lines. Those are not as interesting for this particular talks. But these red, broad red features at 3.3, 6.2, 7.7, 8.6, 11.2, and 12.7. Those are widespread. We see them everywhere. And they're always sort of like a hand sticking up, 5 meters. They're always coming together, basically. And so when you know that the mid-infrared spectra is dominated by these features, then you can also take images in the light of these features. And then that's one way of studying the distribution of these carriers in the interstellar medium. Let me take you through a little tour of the molecular universe. This is a well-known image, of course. This is M42, the Orion Nebula. Here are the ionizing stars, the trapezium cluster. They're ionizing the gas around them. The ionized gas is 10,000 degrees. It recombines. And when it recombines, this plasma creates these beautiful red colors. That's just the recombination radiation from the ionized gas. You see up here, you see some stars, later type stars, B3, B4 stars, which are illuminating their surroundings. They cannot really ionize the gas very much. They just reflect the light of the dust. And so this is the optical. You see some dust obscuration as well. This is what you see in the optical. If we had infrared eyes, what would this look like? If we had eyes that were sensitive to what molecules emit, what would this look like? That's this next picture. You see now, you still recognize this trapezium cluster shining on the cloud, but you see that this whole cloud is now glowing in this infrared, in this red emission, which is basically, this is a false color image, of course. It's a false color image that is centered on one of the strong pH bands. So you see that in this light, in the mid-infrared, this whole cloud lights up because these trapezium stars are illuminating their surroundings, because these stars up here are illuminating their surroundings and pumping up these molecules, and the molecules relax through the emission of the infrared. And this is a scale of, a few parsecs. So this whole region of massive star formation on the scale of a few parsecs is glowing in the light of these molecules. There's another example that I want to show. This is M51, the Whirlpool galaxy. Beautiful whirlpool, if you like whirlpools. Here's the nucleus, and there's these beautiful spiral arms coming out of the center. And you see on this these blue dots. Well, each of those blue dots is basically one of those regions of massive star formation like Orion. Yeah, so this is again an optical image. You see nice dust patterns here, dust obscuration, dust lanes. And what would this actually look like if you looked at it in the infrared, if you looked at it in the light of these molecules? This is what it would look like. You now see that the whole galaxy is lighting up in the light of these molecules. And we're now talking about things on the scale size of tens of kiloparsecs. You see that the whole infrared is aglow in the light of these molecules. And it's not just those regions of massive star formation like Orion. No, it is everything. Everything lights up. So these molecules are everywhere. And they must be abundant because they are dominating the mid-infrared emission from these regions. So they must be important, basically, because of this. Just look at this image, and you know that these molecules are telling you something. They must be telling you something, because they dominate the light. And if they dominate the light, they must be doing something that's interesting. So that's sort of the bottom line that you are going to carry away from this talk. There are all these beautiful molecules out there, and they're affecting their environment, and we're trying to discover both what are the properties of these molecules, and we're trying to discover how can we use these molecules to study the environment, and we're trying to discover what are these molecules doing in their environment. Are they just polluting, or are they also having a healthy contribution to the ecology? Well, this is on, we saw it on the scale of a few parsecs in region of massive star formation. This is on the scale of a few, of tens of kiloparsecs. I'm not sure why it does this, but this is now we're looking at a protoplanetary disk. So this is scale size of the solar system. Here's the star. This is a protoplanetary disk, so this is a few hundred AU. And this, the light here, it's a little confusing, but the green light here is, again, light from these polycyclic aromatic hydrocarbons, but they used a different false color just to confuse us. Yeah, but you see now that the whole surface of this protoplanetary disk is set to glow in the light of these molecules. So these molecules are present in regions where planets are being formed. And they actually form an important part, a dominant part of the organic inventory of these regions. We're talking about 10% of the carbon. 10% of the elemental carbon is in the form of these large molecules. Yeah, and so trying to understand this, trying to understand how these molecules tie into the organic inventory, how these molecules are affected in these regions, how they're going to be tied up into planets, all of these things are the key things if you want to understand the origin of life and how it all started. So that's sort of in a broad painter's background of what we are interested in and what we are trying to do. Let's go back to that to one of those spectra. This is NGC 7027. It's a planetary nebula, and you see here these different features: 33, 62, 77, 86, 11.2, and 12.7. And here underneath you see for a simple polycyclic aromatic hydrocarbon, 2 rings. This is naphthalene. This is the molecule that you all know. If you ever visited your grandmother and she opened her cupboard and you smelled those mothballs, this is what you smelled. Yeah? Yes, these molecules. She has a time-honored tradition, you know. She connects to the universe. You didn't know that about your grandmother, I guess. Yeah, so these are the different modes that are involved, and they're very characteristic and occur at very characteristic frequencies. We talked about that briefly yesterday when we talked about Hooke's law and how Hooke's law determines where your vibrational transition is. It's the basically the strength, strength of the spring constant divided by the mass or the reduced mass of the system. And the square root of that is Hooke's law. That determines where the frequency is. And here is a C8 stretch. So you have the halogens, the white things are halogens, the green is the carbon. You have the halogens stretch in the plane of these molecules. Here you have the CC stretch, and you see that, oh, now the whole molecule is sort of waving like this. And all the carbon atoms are participating in this. Here's the H6 CH in-plane band. So the halogens are not moving, stretching out of the plane, but they're moving like this in the plane. And here you have the CH plane CH out of plane band, so the halogens are moving in and out of the plane. And all of these occur at very typical frequencies. These are very characteristics. From this spectrum, we know that we're talking about polycyclic aromatic hydrocarbon materials. Yeah? It doesn't say anything else. It just says something about the nearest neighbors, because remember Hooke's law, it only talks about the nearest neighbors, about the spring constant, and the spring constant is really related to the nearest atoms that are connected by the spring. Yeah, so that we're talking about molecules is a different story. And that story has to do with basically with the size of the molecule is determined by that it needs to be very hot. Yeah, if you want emission at 3 microns or at 6 microns, you have to be hot. You know, a cold dust grain at 10 degrees in the interstellar medium is not going to radiate at 3 microns or at 6 microns or it will radiate mainly at 100 microns. If you want to radiate at these wavelengths, you need to be a few hundred degrees, 500 degrees or so. And so the idea is that in a tenuous environment where you have few photons around, basically what happens is that your molecule, it absorbs a photon, it gets highly excited for a very short time, and while it's so excited, it starts emitting radiation. And it starts emitting radiation, of course, because, at these short wavelengths because it's so highly excited. There's a high internal temperature. But it cools down very rapidly. It cools down in a second. And then it sits in the interstellar medium. And it's just waiting for that next photon, the next UV photon to come and to excite it again. And that photon comes maybe a year later. And so a year later it is excited again. It starts waving and it starts doing all these things and radiating and having fun. And a second later the party is over again. Yeah? And so the average temperature, if you think about an average temperature is low. Because most of the time, this molecule will be 5 degrees. Because it has no internal energy. It has radiated it all away. But every now and then, it absorbs a photon, it gets very highly excited, and then, that's the moment that it emits. So that's the moment that when we're measuring their emission spectrum, they're highly excited, and we measure their high temperature. That's the long and the short of the... And we'll get back to that point in a minute in a more quantitative way. Let me just emphasize the spectra. They imply aromatic hydrocarbon species. We talked about that. There is this evidence for molecular emission. That's the energetics. I just talked about it. You need to be highly excited in order to be emitting at short wavelengths. And that really can only happen if you're small. Yeah, because if you're small and you absorb 10 eV, then you have few modes over which to divide all that energy. So you have to get highly excited. If you're very big, then you have so many modes to divide that energy over, so you will not increase much in temperature. Yeah, so, and when you work at the numbers, you get numbers of the order of 50 carbon atoms. Yeah, and then another thing is the feature to continuum ratio. If you have a dust material, the feature to continuum ratio is always fairly low. And then there is this anharmonic profile. I will not talk about that. You just have to believe me there. So what are we talking about? Aromatic hydrocarbon structures. So hexagons. Hexagons arranged on a plane. So 6 carbon atoms, and then those are fused. And then the edges are saturated with atomic hydrogen. And the planar molecules, they're like chicken wire molecules. That's the way to think about it. And then we're talking about the typical one will have the order of 50 carbon atoms. Now the biggest one that I drew here is 30 carbon atoms. And you see that this one doesn't have a name anymore, but these all have names. You know, that's why they're interesting, of course. They have names. You know, they're friends. You can take them to the laboratory. Yeah, you can investigate them. No, that's the interesting part, a dust particle. You know, a dust particle is only a dust particle. If you've seen one, you have seen them all. And it doesn't really matter whether you have a million carbon atoms or 1,000,001. But if you have a different number of carbon atoms when you're so small, it really does matter. You can see that these are all very different in structure. And so that's why, from a molecular point of view, but also from an astronomical point of view, you like to understand which molecules are present. We're talking about 14 parts per million of the carbon locked up in these molecules, 14 parts per million with respect to hydrogen. That's about 5 or 10% of the elemental carbon. It depends on which region you're looking at. So it's really very abundant. Think about it. Think about it. Yeah? 10% of the carbon atoms in your body were once a molecule. Yeah, you want to understand what that molecule and what those carbon atoms were doing when they were floating around in the interstellar medium. And they're very ubiquitous. You see them everywhere. We saw those images. You know, they are everywhere. They must be important. You know, they must be important to understand as a constituent of the galaxy because they are so predominant. Yeah?
They would still come mostly from the galaxy interstellar medium and not from other configurations. It's only interstellar medium because the temperature is too low?
Yeah, they would still come from the interstellar medium. We can see that in the nearby galaxies, but also it's just, how should I say that? You know, if you think about the spectrum I showed was NGC 7027, which is a planetary nebula. But there are very few planetary nebulas. And yeah.
In integrated light, these galaxies are
it dominates the mid-infrared emission from these galaxies.
From the gas they have.
It dominates the infrared spectrum.
I'm bringing a microphone.
No, but I think
No, they dominate the mid-infrared spectrum. And so they must be absorbing a large fraction of the UV light. It's just a matter of they must be covering a large fraction of the sky as seen from the stars. You know, and so it can't be a few miserable planetary nebulas that are confusing you. Excuse me. Excuse me. Well, at least you're awake. So this is the outline of the lecture. I'll talk a little bit about thermodynamics because I already mentioned that that's the key to understanding the temperature, and the temperature is the key to understanding how these species behave. I'll talk about how we derive these abundances. Talk a little bit about spectroscopy, the role of powers in interstellar medium, power photochemistry, and power evolution in PDRs. It's a lot that we have to get through. I'll try to be very quick. That means that I'll skip over a lot of details, which is very good for you because then you have questions. You remember the finger of God? Well, the finger of God is waiting to point at you. It's so nice to stand on this side of the finger. So let's start with thermodynamics. I talked about it just a minute ago. I talked about it in terms of a dust particle, in terms of solid state. And really I should be talking about these things as molecules. And the process that's happening is a fluorescence process. Your molecule is in its ground electronic state. It absorbs a UV photon, goes to a highly excited electronic state. This is about 5, 6 CV high. That's the kind of photon it will absorb. And then what will happen is that, say the S4 state, it will convert. It is in one of the vibrational states of this highly excited electronic state. It will convert to a highly excited vibrational state of a lower lying electronic state, and so acquire a lot of vibrational energy, and then eventually it transfers all the electronic energy that starts off with into vibrational energy. Think about it in terms of your Bohr-Oppenheimer approximation. You have your molecule. You have an electronic electron that is reacting to an electromagnetic field, to the photon, gets highly excited, moves way over here, and all of a sudden those atoms that are present there feel a very different electric field. And so they will start to react to that. And they'll start to react to that on the time scale of picoseconds, or tens of picoseconds. And that process in which you convert electronic energy into vibrational energy is what we're talking about here. Yeah, so the atoms in your molecule are reacting to the absorption of the photon in a somewhat delayed way, but you change from this electronic state to lower line electronic states. And all the while that you do that, you convert the electronic energy into vibrational energy. And then you wind up with a highly vibrationally excited molecule. Lots of energy, 5 eV, 10 eV of internal energy in vibrational energy of the atoms. Yeah, and if you think about it, you know, if you have a molecule which has maybe 50 carbon atoms, that means it has 150 degrees of freedom, 150 degrees of vibration. Yeah? And you have absorbed 10 eV, then every vibration will on the average have 0.1 eV of internal energy. And 0.1 eV corresponds to maybe 1,000 degrees. Yeah? So you typically will have 1,000 degrees of excitation in your modes. So you're highly excited, and that's why you emit at those short wavelengths. You can just do a back of the envelope calculation and you get this number out. Yeah, let's talk a little bit about timescales, because I mentioned already that your power molecule will absorb a photon, and how often will it do that? Well, this is the timescale. And it depends, of course, on the absorption cross-section, which we can measure. Depends on how many photons there are in the interstellar radiation field, or the radiation field that they see. And then when you work it out, it is this number divided by the number of carbon atoms, because the cross-section will scale with the number of carbon atoms. And it depends inversely on the strength of the radiation field. And so that means that in the diffuse interstellar medium, you will absorb 1 photon every year. 1 photon a year. In a PDR, you may absorb 1 photon every day. Yeah? And compare that to all the other time scales, that internal conversion, the rate at which you change your electronic energy in vibrational energy is a picosecond. Vibrational emission occurs typically on a time scale of 1 second. So this is the big difference. You absorb a photon, you get an internal energy of 10 eV in once a year, and you emit it all in about 1 second. So, yes? Oh, photodissociation region. Photodissociation region. Yes, it's a. Yes, I'm sorry. It's an acronym that I'm using too much. It's a region of massive star formation where a luminous star is illuminating surrounding neutral material. And if you remember the Orion region that I showed at the beginning, yeah, that's a photodissociation region. And the UV field there is maybe 10,000 times higher than the average UV field in the interstellar medium, and the density is maybe 100 times higher than the density in the interstellar medium. Okay? So it's this discrepancy in timescales that sets the issue. Huh? That's the important parameter. Conversely, what that means is that only 1 in every 10 million pass is excited. Yeah? And most of them are just sitting there, waiting in the interstellar meeting, waiting for to be picked by that UV photon. Please come and excite me again. Yeah, and so I can emit, because that's their goal in life, to be emitted, to be emitting. I'm sorry, I'm getting carried away with my own things. This is some details. We'll skip over that. Look at that if you care to know a little bit more about the things. It gives you a little bit of background. If you have questions about it, you can also come and ask me. So now we have to talk about the power emission temperature, because the temperature, of course, is what sets the emission spectrum. That tells you how much emission you get at short wavelengths compared to long wavelengths. The temperature is also, of course, important when you think about whether the species will dissociate or not. If it's highly excited, it may be able to dissociate. If it is not highly excited, it will not. And let me take you back to probably one of the classes that you hated as a physics student, thermodynamics. I have to take you back to canonical ensembles and microcanonical ensembles. And what the hell was that again? And I wrote you a little primer here. Yeah, so a molecule that absorbs a UV photon absorbs 10 eV of energy. So it has a fixed energy, 10 eV. And so that's an isolated system with a fixed energy is a microcanonical ensemble. And that means the temperature is not well defined, because temperature belongs in the regime of a canonical ensemble, where you have lots of, you have a system connected to a heat bath. And then the system will fluctuate in temperature, because it will take a little bit of energy from the heat bath, it will give a little bit back. And the temperature is then fixed, and it's related to the average energy, but the energy is not fixed. Yeah, so this is the difference between a canonical ensemble and a microcanonical ensemble. And the other difference is, this is easy to calculate, this is very difficult to calculate. And so in thermodynamics, you briefly talk about microcanonical ensemble, but then you quickly realize that if you have a microscopic system, these fluctuations are small, and these two descriptions become equivalent, and the moment that they're equivalent, you say, I'll take the easy one. Yeah, and that's this one. And that's how you describe then all your processes. Now, if you have a small molecule, you cannot always do that, and you have to think about whether you can do that, and you have to think about the density of states. If you have a microcanonical ensemble, then you're not characterized by the temperature. You have a fixed internal energy, so you don't have an average energy, you have no fluctuations, and so you have to think about the density of states. How many states do you have at a given energy? And if you have a lot of those states, that means that you can divide that energy over a lot of different states, and each of these states has a very low probability to be realized. Yeah, that's the definition of a density of states. And I give us an example here. It's not accurate, but it is very descriptive. Consider just as classical oscillators with a frequency. Yeah? And the density of states then increases sharply with the energy and with the number of modes. And it's given here. Here's the density of states. This is the energy. And E over S minus 1 is basically the energy per mode. And you compare that to the average energy, and that's to the power S minus 1. And if this is 10 eV and your average mode is 0.1 eV, then this is of the order of 10 H, but it's to the power 100 or so. So you can see that this is a very large number. Yeah, so the density of states quickly, when your internal energy quickly increases and gets very big. And there are various ways of calculating those density of states. I give a little approximation here, but which actually works, pretty well. We'll skip over that. That's for the aficionados. But you can again see this is the log of the density of states per mode versus the energy per mode. And we're talking here about things which are, this is 1 and this is 2, so this is an enormous number, because 3n minus 6 is of the order of 100 or so. Yeah, and this is the log. So it's talking about something in log which e to the few hundred, which is 10 to the 100 or so. So these are really very large numbers. So you really have what it means is that you have a very large number of states over which you can distribute all this energy. Yeah, a very large number of different ways of doing that, of realizing where you are. Yeah? And then the approximation is the ergodic approximation, which you may remember, Poincaré, another name that you hate. And you basically say the energy is distributed statistically over all the available modes. And every system that can be realized has equal probability to be realized. And so you just count the number of states, and then you can describe your system. Yeah, and then that's the microcanonical ensemble. We can also look at it slightly differently. Let's look at one mode in that molecule. Let's look at one of the CH stretches. That's one of the modes, one of the 150 modes that are present. If you look at that one mode, you can say, oh, that one mode has some energy, and it is in connection with the rest of the molecule, which has most of the energy. And the energy in that mode will fluctuate, because sometimes it will absorb some energy from the other mode, sometimes it will give it back. And so that you can sort of consider as a canonical ensemble. A small canonical ensemble, where you have a fluctuating energy, and you can define a temperature, but and that's much easier to describe. Then the population is what is the probability of having that energy, having this energy in that particular mode, is given by the density of states. Well, this is the total number of density of states. When you have all the states of the whole molecule, and you divide the E, the whole energy that you have over all available states. That's this number, that 10 to the 100 that we calculated just a minute ago. This is the density of states of all the modes except for the mode that you're interested in. And this is for all of the energy except for the energy that you put in that particular mode. So you're calculating here the probability that this one particular mode I has h nu of internal energy. It's just the ratio of these density of states. And that's just counting the number of different ways you can realize these systems. And each system has equal probability. And then in the canonical description, you say, well, the probability that you have a mode with energy E prime, is just given by the Boltzmann factor. And the Boltzmann factor is a factor which sharply decreases with energy. You have a density of states that sharply increases with energy, and that means that you have a maximum somewhere. And that maximum, that means that you'll have a Gaussian basically with a mean energy kT, and the dispersion of that, the width of that distribution, that overlap of the Boltzmann factor and the density of states factor, is basically the average energy divided by the square root of the number of free modes. And so if you're thinking about it in terms of the atoms or the molecules in this room, then you have, I don't know, 10 to 24, 10 to the 25th molecules in this room. That means that you have 10 to the 25th modes. That means that the square root of 10 to the 25th is 10 to, let me take 10 to the 26, that's easiest, 10 to the 13. And your average energy is 300 degrees. So the width of that distribution is the 300 degrees, the average energy, divided by 10 to the 13. Well, that's a very sharply peaked function at one specific energy. And that's why I was saying that for a room like the room that we're in, a microscopic body, you can say that the canonical ensemble and the microcanonical ensemble basically describe the same thing, because you're so sharply peaked at one energy, and the distribution is so narrow. But if you're small, if you have only 100 modes, then the square root is 10, and then you can see that you can have large fluctuations. So that's sort of the background to this. You can, let me skip over this because we're going too deep. I should have made that pink. This is also pink, so we can skip it too. It's good that God invented the color pink. So then we have sort of now a formalism to describe the internal energy and to link it to a temperature and to link it to the excitation of your species. Now we have to think about, well, you have an infrared cascade. The molecule will cool down. As it cools down, as it emits radiation, it will cool down, and slowly its temperature will decrease. And you have to be able to figure out how to deal with that, and this sort of describes that. And now we want to know the temperature distribution function. So what fraction of the time will your molecule be at a given temperature? And that's basically a Poisson process. You absorb a UV photon, and the probability that happens is given by the UV absorption rate. And you get very highly excited, let's say 1500 degrees, and you want to know what is the probability that your molecule has a temperature of 1000 degrees. Well, that is then given by this Poisson distribution, which is given by the UV absorption rate times the time scale that it takes to cool down from the 1500 degrees to the 1000 degrees that we're interested in when we want to define this temperature distribution function. And then you can define that this is for, the example was for 1000 degrees, but you can do that for 500 degrees. You can do it for all temperatures, and it's given by this simple expression. Let me skip this one too, because then in the end, what you get is this. This is time scale, this is the temperature, and these panels are for different sized grains, for different sized molecules. Yeah, and this time scale is of the order of a day. So we're talking about a day in the life of a molecule in the interstellar medium. Yeah? And this molecule, this is small, it absorbs a UV photon, it quickly rises to a high temperature, well in this case only 50 degrees because it's 25 angstroms, and then it cools down. And then it sits there. It's this process that I described. If you're a little bit bigger, this is for a 50 angstrom grain, you can see that you absorb a UV photon, you start to cool down, but before you have fully cooled down, you absorb a next UV photon, and you shoot up in temperature again. You start cooling down, and you shoot up in temperature again, and this process repeats, and you get fluctuations in your temperature, which are fairly large, because your cooling time scale is still faster than your UV absorption time scale. This is 100 angstrom, and now you can see your absorption time scale is now is 750 seconds. And you can see that, yes, you still have some fluctuations, but they're relatively small. You basically have more or less average temperature. And when you're as large as 2000 angstroms, your absorption time scale is 100 seconds, so that on that time scale, your temperature is really constant. This is this effect of having a limited heat capacity if you're small. You're small, then you dump all the heat in the body, which has limited heat capacity, and it has to get hot. Yeah, but if you're big, you have large internal energy, and not much happens. So this is in a graphical way, what the temperature is as a function of time. Here this is shown in a slightly different way. This is the temperature distribution function as a function of the internal energy, and this is for different sized species. And this is the small, this is like a par. And you can see that for a very short time, for a very small fraction of the time, it will be very hot. But most of the time, it will be sitting here, where it is fairly cold. Where it is maybe, in this case, it's 70 degrees, I think. When you grow in, and this is just your Poisson distribution. And when you grow bigger and bigger, you get more and more modes, and you can distribute it over modes. You get fewer and fewer fluctuations, and you go over your Poisson distribution becomes a Gaussian distribution, and that's what you see here. These are basically Gaussian distributions. This is 100 angstrom, this is 250, and here we're talking about a few thousand angstroms. And you're really in a well-defined internal energy with a very narrow width. Yeah, so that's the difference between a solid dust grain and a small molecule. It's the difference between being in a steady relationship with the UV radiation fields or being highly excited. And then with that temperature distribution function, you can calculate the emission spectrum. We'll skip over that, and we'll start to use a little bit of this, trying to understand what's going on in the cell medium. Let's first look at the abundance. And if you think about it in terms of dust, if you analyze dust spectral energy distributions, it's really fairly simple. You measure the spectrum in the infrared, and from that spectrum you say, oh, it peaks around 100 microns. That means that my dust grain is of the order of 15 degrees, 10, 15 degrees. And if it's that temperature, then I can convert the observed intensity into an optical depth. I just divide the observed intensity by the blackbody function. That gives me the optical depth at 100 micron. Yeah, and that is a good measure for how much dust you have. You cannot do that for the pHs, of course, because you only see the pHs that are highly excited. And that's a very small fraction. Most of the time, remember, those pHs are not very highly excited. They are very cold. And so you have to make a large correction factor, and that large correction factor is difficult to estimate. And so that would make this procedure very difficult to do. And so we do it slightly differently. We look at the total spectral energy distribution. We say, hey, this we can separate out, because the dust grains emit predominantly around 100 microns. The pHs emit predominantly in the mid-infrared, because they have such different temperatures. And then we just can compare how much energy was absorbed by the dust and how much energy was absorbed by the pHs. The dust will emit at the long wavelengths, the PAS will emit at mid-infrared wavelengths, so we can separate that very nicely. When you separate that, then you can say, okay, now I know how much UV each of the components has absorbed, and then you can say, okay, I know the UV absorption cross-section. It doesn't really depend very much on whether I'm a solid or whether I'm in a molecule, and so you can directly compare that, and you can derive from that with some algebra the fraction of the carbon locked up in your pH. And you find it's for these kind of numbers, it's about, if 10% of the energy is emitted by pHs, about 5% of all the carbon in the galaxy, all the carbon in the stellar medium, is in the form of these pHs. And so it's sort of a different way that you derive the abundances than for dust, but it is very effective. And then you can do this for different components that are present. I don't want to go into too much of the details. I want to show you this particular slide, which shows the fraction of the carbon locked up in species with a given size. This is the size in terms of number of carbon atoms. This is your interstellar dust size distribution, ranging from about a few thousand angstroms to 100 angstroms. And these are the different emission components that we identify in the spectra. And you can see lots of small pHs and with some astronomical interpretation, just looking at it, you say, oh, it looks like these pHs are just the extension of the interstellar grain size distribution into the molecular regime. Or if you like molecules better, you would say, the dust grains are really the extension of the molecular size distribution into the grain size range. Yeah, and that could just be because the two are really related. Here's your pH, and if you start to combine those, you get clusters. And if you start to combine them even more, you get nanometer-sized particles. And if you sign even more, you get dust grains. And then whether you take those big dust grains and collide them and fragment them into small ones, or whether you take these small ones and stack them into bigger ones, is a matter of which model you want to believe. So let's now talk about power spectroscopy. And here we're talking about infrared spectroscopy of pH, because that's how we can infer something about the species. We see their infrared spectrum, and what is that telling us about the kind of molecules that are present? And there has been a lot of effort over the last 20 years on measuring the spectra of these kind of molecules, or calculating them using quantum chemical methods. And this is a comparison of these different techniques. I don't want to go into much detail on this. I just want to stress that at this kind of level of description, the agreement is pretty good. Yeah, so the different methods, which all have their shortcomings and their faults, and none of them are perfect. All of them have their issues, but they sort of agree if you squint your eyes. And there are now databases available. This is the Quantum Chemistry DFT PAR database, which collects spectra of pHs, and that can be accessed through the web, through an interface, and you can just click and say, hey, I want to know this molecular spectrum. Most of those have been calculated quantum chemically, because that's the easiest method to do. Because if you want to measure the spectrum of a molecule, you first have to synthesize it. And if you synthesize it, well, that's your one master student spent, you know. It takes a master student to make a specific molecule. And master students are hard to come by. You know? You don't want to waste them on synthesizing a molecule. I can see you smile. Yeah. The master students are not smiling. Yeah, so you don't, it's very difficult to synthesize them, and so to measure the spectra in the lab. It's also difficult because the techniques that you have to use are really very involved, really difficult to measure those spectra. And it's much easier to do this in silico, to do it in a computer, because the DFT is just a powerful instrument. You can just easily change the number of carbon atoms, and you just change the structure, and calculate what the spectrum is going to be. And when I say easily, we can now calculate, if it is a fairly symmetric, compact molecule, we can calculate species that contain a few hundred carbon atoms, 300, 400 carbon atoms. You know, we could never synthesize that and measure that spectrum very easily. Yeah, so that's the advantage of the DFT. The disadvantage is, of course, that, well, how wide is it? And we'll get to that point in a minute. But once you have this database, you can say, okay, now I can compare these spectra to my observed spectrum, and I know that there are issues, and I cannot trust the details, and the database is not complete. All those things play a role, but I can still ask questions that are interesting. Like if I make my fit, this is the example of one of those fits, I can say, well, what's the spectrum of the molecules that contribute to the spectrum between 16 and 60 carbon atoms, or between 60 and 90 carbon atoms, 90 and 130 carbon atoms. Or I can do that for the cations. These are all cations, these are all anions, and these are all neutrals. And so I can query the database and select on what is the contribution of different components to this spectrum, to the observed spectrum. And that gives me some feeling for what is going on in the interstellar medium. May not be the definitive answer, but it is an answer. And it's, of course, when you get an answer, you have to think about what does it mean, and how relevant is it, and what are the systematics. But you can still publish a paper. And I have done that, so. Yeah, so, but I said you really have to compare, you have to validate these theoretical spectra. Because your fit is only as good, and your trust in your fit is only as good as you can trust that database. And so most of the initial work in this was based on a comparison between the calculated spectra, the density functional theory spectra, comparison to what's called laboratory here, which is really matrix isolation spectroscopy spectra. So you take your molecule, you deposit it on a cold finger in an icy environment, so it's cold, it's sitting there, and you can measure an absorption spectrum. And there are some issues with that, and there are clear issues, and in order to bring, say, the frequencies into agreement, you have to apply a general correction factor. And we have measured this for a few species, maybe 10 species that this is based on, but we have applied that same correction factor everywhere for all species that have been calculated. Ooh, you can already see that that is an issue. And that there is such a correction factor you can understand. It has to do with anharmonic interactions, because all of these calculations were done in a harmonic approximation, where you assume that the molecule is behaving harmonically. But the molecule is, of course, not harmonic. You know, the molecule knows that this atom is connected to another atom, and that connection will affect the frequency of a mode here. And so that there is a correction factor, we understand, but how good that correction factor is not clear, because these matrix studies have their own issues. You know, if you put something in the matrix, then the molecule is affected by its environment. If it is putting in an ice matrix, it's sitting there nice and tight, and it's difficult for it to vibrate at exactly the same frequencies that it would have if it were free floating in space. And so that's a clear issue with matrix isolation, and that's a problem. And, but we couldn't do much better, so that's what we did. Yeah? And so all the discussions in the literature are based on this kind of analysis, this kind of a correction factor, and people deal with it that way. Now, recently we have started to measure a number of pHs in the gas phase at low temperature. A very difficult and very challenging experiment to do, but we have done that for a number of species. And here we, basically what you do, it's a simple technique really. You have your molecule, a molecular beam, it's very cold. You take a UV laser, it absorbs 2 photons to get ionized, and it has to be in resonance. You know, the first one takes you to, say, the S4 state, and the second photon takes you to the ionization limit. And you have to get from the ground state, where you're in a very specific state, to a very specific state in the S4 state. And that only happens when you're really in tune with that wavelength from that UV photon. And when you're in that excited state, you can be easily ionized. Yeah, and then what you do is you take a infrared photon, and you shine an infrared laser, you shine that on the molecule as well. If the molecule can absorb there, because it has a vibrational mode, then it will pump that species out of the ground state, and that means that it cannot be ionized anymore, and you'll see your ion signal that you detect with a mass spectrometer. You'll see that ion signal disappear. So you have it's called an ion dip technique. You ionize it, and when the dip appears, that means that you have lost the species from the ground state. That means that it has absorbed things. And so that's what these black spectra are. The red spectra are the matrix isolation spectra. And you see the comparison is not too bad. But there are also clearly issues. There are some differences in the spectra and that are present as well. We can go further. This is a comparison of the spectra. This is the harmonic approximation. This is the anharmonic calculation, where it's not only anharmonicity that plays a role. We can calculate that now, that anharmonicity, but it's also Fermi resonances. If you have 2 modes which are very close in frequency, then they can combine. You get the 2 frequencies change into one frequency, which is the average, and one frequency, which is the difference. Yeah, and so that shifts the modes. It shifts the frequencies. And the Fermi resonances can be very important, particularly in this region. I'll show you in a minute. But both of those effects have been taken into account in this spectrum, and we compare it here. This is the theory, this is the experiment. This was a NIST spectrum measured at 300 degrees. And you can see that we do actually a pretty good job in getting all these bands. And remember here, it's this region here, you know, and there are no bands in that region in harmonic approximation, because you don't have combination modes. Yeah, so you do pretty good. The theory actually does very, very good. This is 3 micron region. This is where these resonances, these Fermi resonances, really play an important role. Let me. I didn't show here. This is the experiment. This is the theory. In the anharmonic Fermi resonance calculation, if you were to look at the harmonic calculation, you would have one mode which would be about here. Yeah? There's only one mode, and it is way off. You can see that because of the anharmonic interaction, you get these combination bands. You get that the CH stretch combines with out-of-plane bending modes of the molecule, an overtone of that, and you get many, many more bands. And you can also see that those bands actually shift because of this Fermi resonance. And you can see that the number of modes that you get is a pretty good agreement. The number of strong modes that you get is a pretty good agreement as well. You don't get exact agreement because that's very difficult. You know, if you have 2 modes which are very close in resonance, then shifting one by a little bit is going to make a large difference in the average or in the things. But you have changed from something which was off by 100 wave numbers to something that's maybe off by a few wave numbers. So all of a sudden you have a much better handle on the infrared spectra of these species. And so we have done this now for a few, I think in total maybe 15 spectra, mainly in this region of the spectrum. We are going to extend that to the longer wavelengths, but in the end, this is the way that we hope to validate the spectra in the database. We hope to understand what the anharmonicity, what the Fermi resonance does at a molecular level, at a fundamental level, because we cannot calculate, we cannot measure all of those spectra in the lab. You know, this was, as I said, this was 10 spectra that have been measured, 10 molecules that have been measured, was one PhD student. Yeah? So if we want to measure 100 things, then we have to waste 10 students on this project, and I'll never get the funding for that. So, and I'm sure I'm not going to get students for that as well, you know, because it's not that interesting to be number 9 in the line of students who has measured pH spectra. Well, you can do these calculations much more easily. Yeah, we can now calculate up to, I think, 30 carbon atoms in the anharmonic and Fermi resonance approximation. And I think in a few years that will build up very quickly. You know, Moore's law is on our side. In silico will always win because Moore's law is on our side. And then, as I said, you can apply this to observations, and you can say, okay, I have this database. Let me just say that I trust this. Let me just say what is it going to tell me about the observed spectra. And so what I can do is I can take some observed spectra and I can compare them, fit them with the results in this database. Knowing that there are issues, but nevertheless I can make this comparison. And the first thing what you do, what strikes you when you do this is that these are 3 different regions, NGC 7023, NGC 2023, and NGC 1333. There are 3 different regions, very different parts of the sky. Yeah? These are reflection nebulas, excuse me, these are reflection nebulas. So the regions illuminated by B2 stars, fairly, you know, benign-ish environment. There are no ionizing photons really, but there are photons with maybe 10 eV, 6 to 10 eV that are dominating the sector. And the thing is that these regions have really, when you go to the brightest spot, they have really very, very similar spectra. Spectra are similar at I think it's about the 10% level. That's amazing. If this were due to a large collection of pHs, large collection of different molecules contributing, why would that region in the sky know what those molecules there are doing? Why is that? And so that has sort of led to the idea that, well, maybe there isn't really a large family of pHs. Maybe there are only a few pHs that dominate the interstellar PAR family. A few species which rule the route, let's say the grand PARs. Yeah, so we're hunting now for the grand PARs. And we can now put that into our database and try to see how this relates to what we know. And then so when we do a fit, we can fit each of those spectra, and then we can play a little game. We can say, okay, now we have fitted, and we have, say, 10 different species, 20 different species that contribute to this observed spectrum. Let's throw out the most abundant one that we get in this fit. What is the fit going to do? We refit it, we try it again with the database. What is it going to do? And we find another good fit. It's maybe a little bit less, but it's still a very good fit. But what has happened is that you had a species which observed right smack at the right frequency. But if you remove that species, the database will react by taking 2 other species which have very close frequencies and which add up magically to the same feature. You know, that's not what nature is doing. The database may be doing that, but nature will not do that. Yeah, it's inconceivable that nature conspires to produce the same spectrum everywhere with very different family of species. And so that's what the database is telling us. There's really a limited number of species that can contribute. Yeah? And that's basically because, yes, the spectra are very similar. They're all like, you know, they're all like somebody standing in the bar and saying, hey, 5 beer. everybody has a slightly different hand. And that's what these molecules have also. They're very slightly different, subtle changes, and our spectra and our database is good enough to pick that out. And when you work it out, the abundance variations should be less than about 30%. Another argument that we have is that when you look at the 15 to 20 micron region, then you're not looking at immediate neighbors that are vibrating, but you're looking at larger structures. You're looking at CCC modes. You are looking at the modes that belong to 3 carbon atoms vibrating in a certain way. And those are, of course, much more characteristic for the specific molecule that you're looking at. Then the structure of the molecule starts to play a bigger role. And we actually see only a few bands dominate this region. And when we look at our database, then we find that this is much more a fingerprint region in terms of much more characteristic for specific species. That you only see 3 bands, while if you had a wide variety of species, you would see hundreds of bands which would mesh into a broad feature. Yeah, that you see 3 specific bands means that you have a few large pHs. Yeah? And that's the evidence for these grandpas. And then the last evidence is that we have a grandson. If you have a grandpa, you must have a grandson. And the grandson is C60. And I'll talk about C60 later on. So this is one of the things that you can learn from looking at the database and using that to analyze the data. But you can also say something about the size of the species. And we made that point before, that you have this limited heat capacity because you're such a small species. You have these large temperature fluctuations. And how large these fluctuations are depends on how small you are. Yeah? And that has immediate effect on the ratio of the 3.3 to the 11.2. Yeah, because that's a large difference in large leverage, in energy, in frequency. And so it means that for 11.2, you can still emit 11.2 if you're a few hundred degrees. If you want to emit at 3.3, you have to be close to 1,000 degrees. Yeah? And so the ratio of those 2 bands can be used to infer the size of the species. And this is this reflection nebula NGC 7023. This is the photodissociation region font. So here is the molecular cloud. Here's the photodissociation region font. Here is the star. It's illuminating this font. And I think the black contours are a molecular hydrogen emission. So they delineate this surface as it is being illuminated. And the colors are then the ratio of the 3.3 over the 11.2. And the colors range from about 0.6 to typically 0.36, all the way down to 0.2 or so. Yeah, and we can relate that then, using the database, we can relate that then to the size. And that's done here. This is that same intensity ratio. This is the number of carbon atoms that is present in your species. And this is the ratio that you would get for these different species in the PAR database. Basically, this temperature. Yeah? Small species are much hotter, have much more 3.3 emission. Large species are much cooler and have much more 11.2 micron species. The intrinsic strength of these modes doesn't vary much between these different species. Basically, this is the temperature. This is because the smaller you are, the hotter you will get if you absorb a 10 eV photon. Yeah, then you can see that this range from 0.6 to 0.2 is from these reddish colors to here, these blue. So it is from about 50 carbon atoms to about 80 carbon atoms. So we see in this region, we see actually variation in the size, which is interesting. Huh? There is a star shining on it, and somehow that's affecting the population of the pHs in this environment. And somehow this size changes, and that probably has to do with the UV photons that are present and that are shining on these species and destroying them. So that's one thing that you can do. The other thing that you can do is you can look at the database and look at it and say, what is the spectrum of a given class of species? And this is one example. This is the spectrum that you get if you look at neutral pHs. It has a strong 3.3, it has a strong 11.2 and 12.7. These are the CH modes, the CH stretch and the CH out of plane band. But there's very weak modes in this region, which are the CC modes. If you analyze the same set of pHs and you look at the spectra, then you see that the CH modes are much weaker, but the CC modes are much stronger. And then if you look at the observed spectrum, then actually you see that those modes are actually roughly equally strong. And that means that you need to have a combination of neutrals and ions. Yeah? And that's what this is. This is from the PAR database, just a combination of neutral and cation species added up in such a way that reproduces the observed spectrum sort of at a glance. Conversely, what that means is that you can use the spectra to infer the ionization state. You can infer how many neutrals do I have compared to how many ions. And then you can look at this, at different galaxies. These are different galaxies, and they're all normalized. The spectra are all normalized on 11.2, and you can see that that ratio relative of the CH modes relative to the CC modes varies by an order of magnitude almost, a factor of 5. And so that means that in these different environments, the pHs have different degrees of ionization. That's essentially what it is telling us. Now, the ionization of these pHs depends on two things. It depends on how easily is it ionized by a UV photon, and how easily does it recombine with an electron, the ionization balance. And so it's controlled by a parameter which we call the ionization parameter. You know, we are simple-minded, simple expressions. And it's just the ionization rate over the recombination rate. And the ionization rate scales with the strength of the UV field, which is given here in terms of the Harbing field. And the recombination rate scales with the number of electrons and the electron temperature, inversely with the square root of the electron temperature. And so this is your ionization parameter. Yeah, if you have more UV photons, you're more highly ionized. If you have more electrons, then you're more easily recombined and you're more neutral. Yeah, so it's this parameter that controls the ionization balance, and it's expressed here for a PAR, what the fraction of the neutrals is for a PAR with two charge states. You can recognize this is that ionization parameter. And so we can use the observations to infer what the ionization status of the pHs. And that's interesting because you can then look at a spectrum and take the ratio of the CC modes over the CH modes. That's what this ratio is. So that's the ratio of the ions over the neutrals. And we can plot that as a function of this ionization parameter. And for a number of regions that have been well studied, a number of photodissociation regions, we know what the density is, we know what the UV field is, we know what the gas temperature is, so we know where they fall along this axis. And we can measure this, and so we have an empirical relationship here that tells us what a given band ratio means in terms of the physical conditions in the environment. It means if you have a ratio of the order of unity, then it means that you have this parameter is of the order of 1,000. It means that you have radiation fields which is maybe 100 times more intense than the interstellar radiation field, but a density which is maybe 10 to the 4 times more important than the interstellar radiation field. Yeah, and so all of a sudden you have a tool here. All of a sudden astronomers are waking up, because all of a sudden you can take your observations of a galaxy very far away, and it can tell you something about the physical conditions in the regions that are emitting these pHs. And those are the regions of massive star formation. We saw that in one of the earlier slides. Those are the regions that we're really interested in anyway. There is another effect that comes in because we're talking about ionizing these pHs. And when you ionize these pHs, you get an electron, a photoelectron. That photoelectron takes some of the photon energy and converts it into thermal energy of the electron. The electron comes off, the ionization potential may be 6 eV, you may be absorbing a 10 eV photon. That means that you have 4 eV photon, 4 eV electron that comes out, that collides with collision partners in the environment and is heating the gas around it. Yeah, and that's this electric heating scaled basically with how many neutrals you have, which is basically this ionization parameter, which is basically this parameter that we can measure by looking at the spectra. And then we can make a model for that, for the heating as by the photoelectric effect, as a function of the number of carbon atoms, for a family of PEHs. And then this is the theoretical curve that we get. And it's plotted in such a way that equal areas under this curve give you equal contributions to the heating rate. That means that small species contribute about half of the heating. Species up to 100 angstroms contribute the other half, and species which are the classical dust grains, which are 1,000 angstroms or so, do not contribute at all. Basically because they don't absorb that many UV photons, and also the electrons that they create are stuck somewhere inside the solid and can never find the surface. Now then we can compare this photoelectric heating efficiency. This is the theoretical curve. This is the heating efficiency that we can measure from our spectra, from spectra of the cooling lines, as a function of this ionization parameter that we can measure for these different regions. And then this is what we find. Now these are the observations. This is the theory. And, you know, it's okay. You know, the comparison is not perfect. But then I didn't use any fudge factor to adjust this. It's the good error bar too. Yeah, that helps. Come on, this is the very first time that this has been done. So I'm actually pretty proud, even though that the error bar is larger than the value that we measure. It's a UV measurement. This is the star O per. This is a UV measurement of the level population in a given line, and I think the line is sort of saturated. And so it's difficult to estimate what the actual column density is. Yeah, so if I were a dishonest scientist, then I would have left that figure, that point off. But I'm so honest, you know. Actually, it's a student who did this. The student is honest. Yeah, and there are only, 5 points on this? No, 6 points. And so everything will look good when you only have 6 points to compare. Yeah? You have to do this for many different regions, where you really vary this parameter a lot, and vary other parameters as well, like the metallicity or other parameters that could influence what you're looking at. We haven't done that yet. That's clearly a goal for the future. And only then can we say, oh yeah, now we understand the photoelectric heating by these PEHs. But the basic thing is what I just explained to you. It's this ionization that occurs, that affects the infrared spectra, but that also heats the gas. Let's talk a little bit about the photochemistry. We talked about that these PEHs have to be highly excited in order to be emitting at short wavelengths. And if you're highly excited, they can also fragment. You know, if you put a lot of energy in your molecule, much more than the bond energy, then you can fall apart. And that energy can come from UV photons or X-ray photons. It can come because you're in a 1,000,000-degree gas and you're bombarded by electrons of 1,000,000 degrees, or because you're in a shock, or because a cosmic ray passes by and heats you up. Yeah, then you have to look at what is the probability that you're going to fall apart, and that depends, of course, on how much energy you have, how you can divide all that energy over all the available modes, what the probability is that you have enough energy in that one particular given mode that you're interested in, that you're looking at to break apart. And that gives you then the probability that the process happens, but then you have to compare it to the probability of all the other processes that could happen, like infrared emission. Yeah, and you can do this, and it's... I should wrap up? Yes, thank you. So when you do that, you can calculate what the rate constant is. And you have to measure use this density of states again. Let me skip over this because I discussed this when I talked about the temperature. It's basically the same thing. It's how much excitation do you have in a given mode that tells you whether you will fall apart. And you can express this with a typical Arrhenius expression where you have something like a Boltzmann factor. What's the average internal energy of your mode compared to the bonding energy, and that gives you then the rate at which you fragment. You have to do some small system correction factors, which I will not talk about here. And then you can compare to experiments, but I'll skip over that. This is also pink. No, this is an important thing still to make. This is the rate for fragmentation as the number of carbon atoms for different loss channels. This is where you lose the methyl group. This is where you lose the hydrogen from a methyl group. This is where you lose, the hydrogen, the aromatic hydrogen from your species. Yeah, you can see this is the infrared cooling rate. And so if you're much faster than the cooling rate, the process will happen readily. If you're not, then the process will not really happen at all. And so if you're small, you get more highly excited, it's easier to fragment. And if you're only a little bit larger, you're actually stable. So it's a very much a flip-flop situation. If you're a little bit too small, then you will readily be photodissociated. And the other thing is that the weakest link will go first. Yeah, the one with the lowest binding energy will be the one that breaks first. So then we have to talk about the power evolution in photodissociation regions. And I first want to go to this particular spectrum. It's actually the spectrum of a planetary nebula, again from about 5 to 20 microns. And you can see that it's very different from the spectra that I showed at the beginning of the PEHs. It's a very different spectrum, and there's strong bands at about 18.9 and 17.4, and there are some weaker bands elsewhere. And when you put this to the spectra, then you find that this is the spectrum well reproduced by the spectrum of C60. C60 is the sucker ball molecule. You know, it has the 60 carbon atoms which are arranged in the form of a sucker ball. I'm sure that all Brazilians have this on their nightstands. I'm sure. Not they grow up playing with this. Yeah, so in this particular nebula, these bands really stick out, and it's clear that you have a region which is dominated by these C60 molecules. Once we saw this spectrum, we went back to all the other spectra that we have, and we realized, oh, this must be the telltale signature of this C60 molecule, and we find it in other places as well. And so this is one example. This is again NGC 7023. So this is the reflection nebula. Here's the cloud. It's this reddish glow. Here's the star. It's illuminating this photodissociation region here. And then there's a cavity here. And so the cloud is shining on this. And we have taken spectra over this region. And then we can analyze those spectra. And we can look at those spectra. And here are two examples. This spectrum is from far away from the star. The star is over here. This spectrum is from far away. It's dominated by the PEHs. But when you get closer to the star, you see these C60 bands coming up. Yeah, what you just see from this is that you can then make a false color plot again. Yeah, where you color the PEHs green and the C60 you color blue. And you can see that there's a clear separation where these species are. The pHs are predominantly far from the star. C60 is much closer to the star, and this is where the main dust is. You can quantify that. You can get abundances the way I described earlier, and this is the fraction of the carbon in the pHs as a function of distance from the star. So the star is over here somewhere, and far from the star you have a lot of carbon in the pHs of the order of 7% of the elemental carbon. But when you get closer, you see that it disappears. Fewer and fewer carbon atoms are in there. The abundance decreases. Yeah? When you look at C60, you see the opposite actually happen. You see that far from the star, you actually have only 10 to the minus 5 of the carbon in these C60 molecules. But when you get closer, you get up to a few times 10 to the minus 4. So you see when the pHs are disappearing, the C60 comes up. And so this has suggested that there is an active photochemistry taking place. As the pHs get closer to the star, they get destroyed by the strong UV light, and some of the pHs that are being destroyed are being transformed into C60 molecules. And so in a global sense, this is what is happening, the two processes. Here are your pHs. When they are exposed to UV photons, you strip off all the hydrogen. That is the weakest link. You form graphene, and that graphene will then, once you have stripped off all the hydrogen, you will start to lose carbon atoms. So you'll move smaller and smaller flats, eventually rings, chains, and then carbon atoms. But while you're breaking it down, While you're fragmented, you can also have isomerization taking place. You can have that those sheets start to fold up upon themselves. They can start to form these kind of cages, and they can isomerize to these fullerene molecules. So the product of this PAR photolysis from this simple kind of considerations is small hydrocarbons, small cages, and PAR fullerenes. We can compare that to our experiments. This is an example. We have an ion trap in which we store large PAH, cation PAH, and then we shine a UV laser on it for a short time. Then we open the trap, and we lead the ions into the mass spectrometer, and we count what the fragments are and how many fragments we have of what mass. And that's what is shown here. Here we start off with hexabenzochoronine, C42H18, the cation, of course. And then when we irradiate it with UV laser, you can see that we start to lose hydrogen atoms. And actually, there is this pattern where the even hydrogen atoms are more abundant than the odd hydrogen atoms. But eventually, you wind up with the pure carbon cluster, and then you start to fragment to smaller and smaller carbon clusters. So you first strip off all the hydrogens, then you start to lose carbon atoms. And here that is very clear. Here we shine, this is at, let me see, this is 5 millijoule, this is about 50 millijoule of your laser energy. And you can see here is your starting point. Here are those hydrogens that you've stripped off. This is the pure carbon cluster, and these are 2 carbon units at a time. And so you break it down until you have C32, and that's the smallest cage that you can form. At that point, the cage will break and open, and you will form chains and rings. And that's over here. And you have hardly anything in between. Yeah, so you absorb many, many photons, you do many, many pulses, and as you do that, you strip off first the hydrogen, then you lose the carbon atoms, you make these graphenes, and then they start to make these cages. And this is an experiment done by others, where they look at slightly different situation. Here you have a graphite surface, and on it there is a little graphene molecule, and it's hard to see. So that's why we have these frames underneath so that you can recognize what it is that you're seeing. Yeah, but they are illuminating this with an electron beam in this case to see what was happening. And the electron beam, of course, deposits energy in it, also strips off carbon atoms. And you will see that what will happen is that the graphene will start to lose carbon atom, it will start to roll up into a cage, and eventually it will form C60. So let me start this movie. Here you start to see, you start to lose them there you start to form that cage. Yes, there's the cage, and there is the football. Yeah, and it's rolling over the surface. And at this point, I must have the attention of all the Brazilians. You know, imagine what this is. This is the smallest soccer game in the universe. And it's easy to imagine Brazil as the soccer champions, but the soccer champions of the universe. That's what you should strive for. Yeah, and of course we call it a soccer ball because it is really, this is the structure of that molecule. Yeah, the carbons at all these hexagons and at these pentagons. Yeah, and here is that illustrated in a artist impression of the process that could be happening. You have a graphene sheet, you strip off a carbon atom and you form a pentagon. You do more, and as you do more pentagons, you have to roll up. If you put a pentagon in a structure, it has to roll up. And so that's what's happening. You roll it up and you form your molecule, your fullerene. And there is some experimental evidence that this is happening as well. I'll go very quickly through this because I'm running out of time. These are some different species that we isolated in our trap, and we shine on it with a different laser. This is a laser at 355, and what happens is that you strip off carbons out of your fullerene, and you strip off 2 carbons at a time, and as you do that, your fullerene will shrink and shrink, and will get smaller and smaller. And you get to see these magic numbers. Some are more stable than others, and that's why their abundance is a little higher. Yeah, you see that for C60. Here's C70. You start off here, and you start to break it down, and you see that C60 is actually a fairly stable molecule, much more stable than its neighbors, and so it is very abundant. Yeah, and if you take your pHs, you do the same thing. You start to strip off first your hydrogen atoms, and then you form these clusters. And again, you see that C60 starts to pick up here, and likely you have formed something which is very abundant. And we can do this at different wavelengths. This is at 532, and 532 nanometers is a very interesting wavelength because C60 doesn't absorb at 532. So if you put C60 in that ion trap, nothing happens. It just stays as C60. And if you take C70, you start to strip off 2 carbons at a time. It's happily absorbing until it reaches C60, and then it stops. Because the C60 is the buckyball, and it doesn't absorb UV photons. If you take your pH, if you take a big pH like this one, you can see that you start to lose carbons at a time, but you can see that there's a large fraction that remains like C60. So we think that this is evidence that you actually have transformed these graphene sheets into C60 and are present there. The sum of the C60 does not summarize and breaks down to smaller and smaller species, but about 25% of the C66 that we started with stops at the C60. For a smaller molecule, that doesn't happen because you have to start losing carbon atoms before you can roll it up into these buckyballs. And so if you start with C60, you can never make a C60 buckyball. But you can make smaller buckyballs, smaller cages with that kind of a structure. So let me skip over this. And this too. This is details on the kind of processes that can happen in it as well. But it's getting late. It's time for coffee for me. And we should go. Really, let me do this last little point that I want to make. Because you have to put it into perspective. What does it mean in astronomy? And this is one calculation that shows that this is for 2 different molecules, circumcoronine and circumcoronine, C54H18, C96H24. This is strength of the UV field. This is the strength. This is the number of hydrogen atoms, and these different colors indicate what species are abundant. So this is pure cluster, C54. If you have a lot of UV photons and few hydrogen atoms, then you will easily fragment, and you will easily form the pure cluster. Yeah? But if you have a lot of hydrogen atoms, then you never strip off all the hydrogens, because there's always a new hydrogen that you put on. Yeah? And so the abundance of the pure cluster is very low. Here is the regime where you have the pure, the C54H18, the circumcoronine itself. It's abundant in this range of G0 and densities. If you go to too high hydrogen density, then you can actually stick extra hydrogens onto your pH. And that's what's shown here. You can get extra hydrogens on it. Now, this kind of behavior depends on how big you are. If you're much bigger, then you really never can fragment into a pure cluster, because you never get excited enough. You have too many free modes over which you can divide all the energy. You never get highly excited. So they never go to these, under these conditions, to these kind of clusters. And then we have to compare that, of course, to what are the typical conditions in an interstellar regime. And this is where you find the PDRs, where you find the interstellar medium in terms of G0 and density. And you can see that, yes, in a PDR, you can dissociate your circumcoronine, but not your circumcoronine. So this is where you would form your fullerenes, but for the C96, you would not. It's not really that relevant. And let me skip over this, and let me go back to this particular slide that I showed the very first lecture. We have talked now about the both building up molecules from small to big, where you take atoms, put them together into bigger and bigger molecules, which you then lock up into your comets and asteroids and bring them to the Earth. And we have now, today, we have talked about big molecules coming from carbon stars, which are ejected into the interstellar medium, broken down to smaller species, and then locked up in comets and asteroids and brought to the Earth. We have talked about some of the processes that play a role in this, and this is sort of a summary of that. And that brings me back to the take-home message. We have gone over that. pH molecules are very abundant. They're ubiquitous. They have typically 50 to 100 carbon atoms. They're excited by UV photons. They relax through infrared emission. They are key to ionization. They are key to the energy balance of the interstellar gas. There's a rich top-down chemistry. You can convert these pHs into fullerenes, but also into smaller chains and smaller hydrocarbons. And, well, this part I have not talked about at all. So the last thing I have is these 2 slides with exercises for you to look at and to see whether the material that I presented today has really sunk in. And I think that if you look at these questions and you look back at the slides, you should be able to address these questions. And if you can't, well, that's a good way of talking to me. And that's, I really was inspired. Yeah. So, but that's the last one. Thank you.
We're going to make time for a few quick questions. I have questions, but I'm giving you a chance.
If you don't have questions, we're going to divide you up into groups again.
And the finger of God will point to you. It's coffee break, and we have some posters, so that's why I was saying. Sorry. If you have a quick question, you can ask it.
It's just a really quick question then. In the time where you said that spectra of bright spots of different reflection nebulae can be remarkably similar, it's just a little technical question. You said that they are very angularly separate, the 3 different that were observed. Are they very spatially separate too? Are they far from each other? Or are they like, it could be a solar neighborhood effect?
No. They are really very different parts of the galaxies. One of those nebulae was NGC 2023, which is in the region of Orion.
Okay.
It's about 500 parsecs.
Region,
The other one is NGC 1333, which is at 100 parsecs in the Perseus cloud, which is, very different. And then the third one was NGC 7023, which is, very, very far away. Very different part of the galaxy.
Okay, so when the PA molecule is being rolled up to form fullerene, would it be possible to an adsorbed molecule in the PA would be trapped inside the fullerene molecule, like a clathrate?
Wouldn't that be interesting? Yeah, it would be very interesting. But in order for that to happen, the molecule, the species has to be stay adsorbed. And if the bond energy is fairly low, then it will come off, before it starts losing carbon atoms. But there are other ways. I didn't talk about that. There are other ways of starting to roll up things. And we should talk about that separately because it's very interesting. If you could roll it up and you could lock a species inside, wouldn't it be fun? Isn't that what we all want to do? No?
It's actually,
Do you believe is it possible to find also those carbon microtubes that are related to the buckyballs, but they are like rolled?
The reason that we see that we can identify the buckyballs is because the spectrum is so different, and because we have this one particular region which is so different from all the others. And we could compare that to the measured spectrum of the buckyball and say, oh yeah, this must be the buckyball. Yeah? And this is a very unique spectrum. And to get these nanotubes, what you are thinking of, to get nanotubes, the spectra are similar, but there is no magic number. The thing is, the C60 is a magic number. There are only 60 atoms that fit onto a soccer ball. And a soccer ball is, in Brazil, it's like God, so it's sacred. Yeah, and there is nothing like that in a nanotube, so there's not a single spectrum that you can point to. Oh yeah, that must be it. Okay.
We're going to have a few more moments for the questions, but I'm going to ask for Felipe Fantuzzi and Natasha Zanon Daneto to come and start setting up your poster area, your slides, yeah, with Laurie. Huh? Sure, sure. So meanwhile we can actually continue asking more questions to Tielens. So while you're warming up, I'm going to continue warming up.